what is Ferranti effect and how it is produced. So before going into the deep discussion, we should know what is Ferranti effect. The Ferranti effect occurs when the voltage at the receiving end of a long transmission line is higher than at the sending end, particularly under a light load or the no load condition. This is contrary to the usual expectation that the voltage drops along the transmission line due to a resistance or the reactance. What are the components used in this diagram? At the sending end, voltage is given 32 kV, represented by a transmission tower on the left with the lines extending towards the right. At the receiving end, we have the voltage that is 32.24 kilovolt, represented by a transmission tower on the right with lines extending from the left. So what we have observed from here, the voltage at the receiving end, that is the 32.24 kilovolt, is higher than the voltage at the sending end, that is the 32 kilovolt. So it shows that a 0.2 kilovolt increases. So already I have talked about the Ferranti effect, that the at the voltage at the receiving end of a long transmission is higher than the voltage at the sending end. So how can we explain the Ferranti effect? So first, capacitance and inductance. Transmission line have inherent capacitance and inductance. Capacitance is the ability to store electrical energy in an electric field, while inductance is the ability to store in a magnetic field. So these properties are distributed along the length of the line. Next one, that is the voltage rise mechanism. Under the light load or no load condition, the charging current due to the line capacitance dominates. This charging current leads to a voltage drop across the line inductance which is additive to the original voltage. As a result, the voltage at the receiving end increases compared to the sending end. So conditions for the Ferranti effect. First one, more pronounced in the long transmission line, typically over the 200 kilometer, and it is noticeable under the light load or the no load conditions. So if you're talking about the mathematical representation, the voltage rise can be expressed through the complex equation involving the inductance, capacitance, and the length of the line. So simplified, the voltage at the receiving end can be higher than the voltage at the sending end due to the capacitive reactance of the line. So what are the practical implications? So first one, power quality. The Ferranti effect can lead to the over voltage condition, potentially damaging equipment at the receiving end. Next one, voltage regulation. Utilities must consider this effect when designing and operating long transmission line to ensure stable and safe voltage levels. Third one can be the mitigation measures. Use of the shunt reactors to absorb excess reactive power and the control voltage level. Ensuring appropriate loading on the transmission line to minimize the effect. So lastly, what we have concluded from the above discussion is that this diagram effectively illustrates the Ferranti effect by showing a higher voltage at the receiving end compared to the sending end in a transmission line. Understanding the effect, this effect is crucial for designing and managing long distance power transmission to ensure system stability and the equipment safety.